I hope what I'm going to do is talk about a topic that doesn't get a lot of focus, but we all know it's a big problem, which is industrial, particularly industrial runoff. I've spent a little bit more time on this presentation than I probably should have on the industrial side of it, and a little less on the highway side. But they're both challenging situations to deal with stormwater management, especially in something like this watershed. I'm from Penn State, Harrisburg, live in the Middletown area. For those who have been out that way, and somebody asked me when I moved there, I'm conveniently located between 3 Mile Island and Hershey Chocolate. And about halfway between both, so the chocolate glows. But the idea is that I'm also on a campus where we took the clean side of the old Air Force Army base and we gave the dirty side to the airport. So, you know, I'm in an area that's heavily developed, just like a lot of this area, just like we just saw in the presentation. A lot of industries, a lot of older industries that are sitting on our water bodies and are really now trying to look at stormwater management and stormwater cleanup, to me, without a lot of guidance is what I see it as. So that's a lot of our challenge. And so again, we're gonna try the smartboard thing. This is not what we have at home. We are an old Army base. We're doing good if we're still, like, it looks like a military base. And we can take a look at that, and I did not pull any in the local watershed. I figured I'd protect them and pick on my watershed. But you can take a look at any of these facilities. This is just up the road from me. And again, that's actually where I used to live until I moved a few years ago. And again, even the highway facility here with our maintenance yard. And I'm glad to see the salt is well contained inside the salt dump. You know, that little white blotch there, yes, is definitely not where it's supposed to be contained. But you take a look at all of these sites, and these are very common in many of our areas. And you can see the basic commonalities are, and the ones we're really concerned about is anything that's got outdoor operations. Large roofing sections, particularly old industries, are notorious for having large galvanized roofing. You know, airports are notorious for it. There's been some challenges with that, and anything like so they're storing outside. Done work with like you know, paper recyclers. A lot of that's done indoors, so it's no worse than a commercial area. But you really take a look at something like this, old steel mills. Take a look at scrap yards, others like that, highways. You are looking at in areas that are heavily developed. This is a lot of it now. It's abandoned. They now have plenty of space for stormwater management, if they did. But they've used most of the land space. So we've got a challenge with a well built out site. We've got a challenge with a dirty site. We've got a challenge with buildings and outdoor operations where we could be getting hydraulic oils, where we could be getting metals, and a lot of that. And so these are that challenge. And they're looking at treatment that is potentially much different than what we are thinking about as we build or retrofit into a neighborhood or a subdivision or a shopping center. So again, I'm going to spend a little bit more time looking at that. And again, that's what we ended up looking at. I did look at, we were setting up a project, looked at a industrial site in the city of Harrisburg that had some outdoor operations. I went by, looked at it. It was part of a large national project, and they asked them, said, how do you treat your stormwater runoff? Oh, it collects in puddles and evaporates. That was their stormwater management practice, was evaporation. They also were sitting on Paxton Creek, and they regularly flood, which I think is how they clean the site. So, you know, that's, you know, like, well, that's how, DEP hasn't said anything. I'm kind of like, okay, we'll leave it right there. But it was one of these sites that, like this, was fully built out, and they're really, short of going underground, wasn't going to be a lot of space for treatment. They didn't have on-site space or off-site space they could deal with. Highways, being very linear in many cases, are running up on their right-of-ways or having trouble trying to deal with linear treatment or moving water off of the highways. Again, to try to get it to some place they can actually treat this runoff. So taking a look at, this is just general urban runoff quality. They don't look, I mean, yes, there are things to be treated in here. They don't look so bad. All of our metals are in the microgram per liter range. You know, it's not so bad. We're pushing this. This is out of this National Stormwater Quality Database. But this is not industrial runoff. This is not highway runoff. Most of these sites are residential and some commercial. You know, so that's where this is all driven from. And the treatments that are being used for that are much, much different. Okay. But here's and I will pull this back in. This is a project we did several years ago at an industrial site in Southern California. I can talk about this one publicly because it actually, the report's published and they're still paying the fines. But no, it's actually an old DOD, DOE site where they had the first nuclear explosion and reactor blow up in this country. So in the 1950s. So again, it's a It's great. It's in a book called, it's also written in a book called it looked good on paper. Stories of Historic Engineering Failures. I did quit reading the book at Plains because I hate to fly. But to give you an idea, they're in Southern California, they're in the Los Angeles area basin. They have a permit. They have a numeric discharge permit for these pollutants. And every time they violate their permit, they write a check to the regional water quality, the water quality board.
It's cheaper to pay the fine.
No, they pay the fine. Well, now what they want to do is design a treatment system to actually not keep paying the fine. Now, to pick on California, because I can, they're not here. They actually did not even have an out clause for an act of God storm for massive flood. They had to pay every single time. But take a look at that and see. These are not things that we typically think about treating for. You know, lead, mercury, zinc. I'm not getting into thallium, uranium, strontium, radium. I've never had to deal with treating for radionuclides before, but we had to actually test for radionuclides. They actually had permit limits for radionuclides. Welcome to being the first nuclear explosion. We were in the buffer zone too. So again, here's our thing, and perchlorate, something we don't even think about being in stormwater runoff. They also have a challenge, and I'll mention this quickly. Dioxin was a permit. Their discharge limit for dioxin was 2.8 times 10 to the minus 8 micrograms per liter. The forest fires generated concentrations higher than that. But that was the choice. They had to design a treatment system, and it's actually out there. It's Boeing Santa Susana plant. You can actually go online and look at the data. But looking at trying to design treatment systems that would do this. But again, and we're going to get into this in a little bit, what works for some of these doesn't work for others and actually causes more problems. So what you have to do is figure out what's your first challenge. What do you really need to treat for to make sure you're in line with the permit limits? And how do we know that? How do we know that, and how do we deal with that? We got to keep wanting to wander back to the computer. Welcome to classrooms. So I went to the state manual and took a look. This doesn't give me any help whatsoever. The permit problems I've got in most industrial sites, if I go back and pull up that picture back of those old abandoned steel mills, and some of it's actually still operating, that's not the problem. Do you see anything out there they're fertilizing? Nitrate is not really a huge problem for them. Their problem is metals. Their problem is oils. That's not what they're doing. I mean, again, the manual is written for a different set of conditions that are probably land-wise much more common, but are still they're not the challenge we're dealing with. So again, TSS, TP. TSS actually helps me. TP and TN don't really help me. I don't have that. That's not where I'm violating my permits. But there's no permit, no discussion in the manual anywhere talking about copper, zinc, lead, mercury, PAHs, whatever it is, petroleum hydrocarbons, all of that stuff is not in there. So again, these are not my permit problems. And so of course what happens, and this is, I did this several years ago, and I probably still like it way too much as a slide. We have this happen. We have a nice little lot, industrial site. We have a bunch of guys show up in a suit and sell you something. Because again, it's got to go underground. They usually start getting into, maybe you have to get into manufactured devices. We have a treatment device. They go away. It rains. You get runoff in there. Sun comes out. And hopefully we get clean water. And so the real question comes in, what happens in the middle? And having worked with some of them, I'm totally convinced. But really what's going on, and we can take this concept and apply it to anything else, is this idea that there's a lot of different things that could potentially be going on, some combination of a variety of things going on, everything from settling solids to chemical reactions to make solids or flocks bigger that'll settle easier, to simply looking at running it through a filter, a variety of different media types that will help address certain pollutants, to even microbial transformation. And I'm not going to talk about plant uptake here because I'm really thinking about industrial sites where we're really not talking about areas that you're going to have a lot of plantings. So there are very few sites, unless they plan for it, that have space for huge ponds and that are going to be ponds in vegetated systems. So again, that's kind of what I wanted to talk about. So it's my Mickey Mouse slide.
You're talking about bacteria.
Yeah, bacteria, microbial transformation bacteria. And that's still going to be very common. Birds don't stop doing what they're doing just because it's an industrial site. Bacteria often is usually not a problem in that. Just again to give you an idea to come through again is that we basically what I want to sit there and emphasize, particularly on industrial sites, they are so varied in terms of that we're trying to categorize them and characterize them by operation. You know, highways are different than scrapyards, are different than potentially airport facilities, are different than that in terms of what you can expect for pollutants and what you can expect for runoff in terms of concentrations. So again, this kind of idea is that basically what you need to do is characterize it. And I just threw up, this is that site in California. Historical data, historical data. Yeah, Michelle.
Is the zinc from the roof, and is the lead historical, or you know?
They are. This was actually outside of. This was a buffer zone area. But yeah, airborne deposition is what they really figure is a lot of airborne. Because again, the area where they blew up the reactor, we weren't treating. It's an old DOE, I mean, again, it's a DOE, DOD site. They tested rockets, they tested rocket fuel, historical concentrations in the soils, you know, airborne deposition. Take your choice for the site. They're in the middle of, they're trying to clean up. What they wanted was a treatment device that would last for 10 years. Because in 10 years, they were turning it over to the state as parkland. So they were cleaning up. There's a separate cleanup for the absolute functional areas of the site. Okay. So there was a separate total cleanup in terms of cleaning up the radioactive material, the old reactors, the jet fuel pads, the rocket fuel. It was 3/4 DOE, 1/4 DOD in the 1950s. And, yeah, so take your choice. So yeah, I mean, again, roofing certainly would be there. Historical lead from gasoline, they made back in the 50s, 60s, and 70s, lead as an anti-knock compound in gasoline and in fuels. And a lot of our, if I remember right, a lot of our fuels still have, some of the high industrial fuels have lead in it still. If I remember right, I don't know if NASCAR still is running on leaded fuel, but for years, it hasn't, if they were discussing trying to take lead out of the NASCAR fuels and they weren't sure they were going to be able to do it. So there is still leaded fuel out there. Diesel fuel's got some, I'm thinking they're trying to get away from some of, yeah, but there are, you know, but lead has not gone away as an anti-knock compound in fuel. It just isn't in our automobiles any longer.
They replaced it with MG.
Yeah, which caused a bigger problem. Caused almost as big, if not a bigger problem. Yes, MTBE was not exactly, as an oxygenation agent, it was not exactly the world's best choice in terms of understanding its long-term environmental consequences. But you know, we're really good at solving a problem with creating it with a new problem. I'm determined at that. But
it creates jobs.
It does. I've been employed for years. So, but what I want to do is kind of give you a thought. Here's that idea of, you know, what are we dealing with here? You know, what we're dealing with in here. You know, again, almost 1 milligram per liter of zinc. We're dealing with, you know, again, and most of our river quality, our river numbers are about 120 micrograms per liter is a rough concentration coming out. The site discharge limit I think was 140. But you know, we're well above that. That tells me what I've got to begin to look at. And again, we're starting to see that coming on these industrial sites. First thing I'm going to want to do is think about the solids part of it. We're going to start talking about how to set up a treatment system to think about it. So first thing I want to do, solids are not solids. They're not like they're all like grains of sand coming off. They're going to have a range of particle sizes coming across a wide variety depending on what they are. This is some old residential work. Here's the few highway samples we have from John Sansaloni on his I-70 work in Cincinnati. I think it's I-70, no, it's not 70. I-64 work, I think it was, in Cincinnati. You know, here's some street dirt, quite a bit of street dirt analysis that was been done around the country. And, you know, New Jersey DEP simulant, kind of give you some thoughts about that. And scrapyards, because we had some nice scrapyard runoff back from the 70s we could look at. But think about that. Here if I'm looking at sedimentation, I'm starting to look at, again, you know, where is my 50% removal? What can I do to get 50% of the mass out of that water? What size particle do I need to control for? How fast does it settle? Have you ever taken dirt or clay and put it in a glass of water and shaken it up? How long does it take to clear? Depends on what it is. If it's clay, it's not going to clear in any reasonable amount of time. So again, we can settle the big particles out fairly quickly, but we may not be able to settle the small ones out. So really we need to know, what are we dealing with? What are we trying to accomplish with this? You know, so again, because the first thing we want to do, the easiest thing, if you think about a water treatment plant, first thing we do is settle the solids and get them out of the way of the rest of the treatment. We don't want them to clog things up. We don't want them to tear up the pumps. We don't want to do any of that stuff. We want them out of the way.
Do you do a component analysis to figure out what percentage of silt, sand, clay?
Well, that's what this ends up being, because this is all particle size coming across and the percent below that. Did I break it apart into those traditional fractions in this graph? No. I'm going to talk a little bit more. We're talking about getting into, to go back to your question, using a different way of getting at clays. But we're talking about easily settleable solids that we could do in something like a small forebay or detention pond or a rapid treatment device that some manufacturer would sell you. We're going to be in the silt range to kind of give you an idea.
Made some type of particle size analysis to do that.
Right. Right. Again, this is probably, I'm a researcher. We can get a little bit more detail without a lot of money. Graduate students are cheap. So, but that's the general idea with that, is to try to deal with that. And I'm going to get to that point. So to kind of give you an idea of looking at just simply two different storms on the same site. Again, but if I take a look at it and saying, if I want to get rid of 90% of my particles, I need to be able to get down between 2 and 5 microns. Those don't settle. We're in the clay range. If I'm going to settle them or hope to settle any of them, I'm going to need a very, very big space. I'm going to need a lot of land area, which most industrial sites, highways, do not have. Again, if I want to get to 50, 80%, I need to 5 to 10 microns. 10 microns, I can begin to settle in a reasonable amount of time. They won't do as easily in a quick forebay, but a decent sized forebay without sacrificing a lot of space, or an underground manufactured treatment device often will do that. So again, I can get to that point. Is that where I need to be? And there are a lot of curves out here. I'm not going to spend a lot of time in there, but it gives us an idea of giving us flow rates for what size device do I need. And you go to the manufacturer or whatever and say, I need this size device, I need to size it, and I want to do that part of it. Again, coming back in, next slide, I hope I didn't delete it. Oh, apparently I did. We're talking in this range, coming up in about 10 gallons per minute per square foot. And that gives you a sizing range, and that will get me out into the larger particles in 100 microns. 20 is I'm going to need to come back in and come across more like 1.6 gallons per minute per square foot.
Is it log normal distribution?
This is, they're both log normal. Yeah. Yes.
My understanding is that toxics tend to attach themselves to sediment. Is that more the smaller size?
We're getting to that part. You're jumping ahead. Okay. About 2 slides. Sorry. And that's the interesting question for different ones attached in different ways, and some of that is site specific. And so, but yes. So yes, you're jumping ahead. So now, but to get into then, if I need to get into the smaller particles, now I start talking about filters. Whether it's sand filters, do I look at a compost filter? Do I look at activated carbon? We've had some people look at activated carbon things. What am I looking at and what do I get to? But to get to those smaller particles in a reasonable amount of time and a reasonable amount of space. Again, thinking about land space, whether it's underground or having to take a corner. That's good. So again, that idea coming back across. And to kind of, again, going back in to kind of summarize again, we really look at the big particles we can probably do with a sump, a vault, a forebay will get us somewhere. We'll settle out a lot of those big solids. We get into the small solids, we're going to have some challenges. We get down here, and we're going to get to that part you asked about, associations of metals and other pollutants. If we have to be in this range to get those guys that are associating with a very, very small solids, we're really if we want to say with physical separation only, we're really looking at membranes. I don't know about the rest of you, but I'm not looking at an industrial site. I don't have any industrial owners that want to pay for the cost of electricity to run a membrane system. So I've got to look at now how can I look at my media and try to use the chemistry behind it to pull those pollutants out. So that's kind of where we're headed for as you're jumping ahead. So it leads into a very, very good question, because here comes the question, which is what's associated with those solids. If I settle those solids, what else can I remove? Because obviously if I can get the solid separation is the easiest piece of that. It's the cheapest piece. Gravity works for us. Gravity works for us whether the power's on or off. And again, we run the stuff underground, we run it through, it works very nicely. But again, we take a look in there and see, the total suspended solids in this correlate well with zinc, with lead, phosphorus, but not with copper or dissolved phosphorus. So again, in some of those, again, it's what we're taking a look at to see. So which ones correlate? Now, some of that, this is an overall analysis of the stormwater quality database, but site-specific wise, we're going to see some interesting differences. And this should give you an idea of that. The first column is basically the entire sample, what I call a total infiltration. You simply run it through and analyze. This is what's less than 20 microns, 10, 5, 3, and less than 0.45 are basically dissolved. This is from an industrial site. In fact, I was processing the data last night. And you can begin to see that we're actually in pretty good shape for a lot of these, and this goes back to your question. For a lot of these, and some of these metals, we may actually be okay if all we do is settle them, because the metals are associating very well with larger solids on this type of site. Again, because you can see, again, this drops very quickly once we get past 20 microns. 20 microns is easy to settle. We can get, that's the sedimentation basin, or a forebay, or whatever. Upflow filter sold by a couple of manufacturers. We can see it with one of our local guys of TerraClean sells. I mean, their treatment devices all work. That's very nice underground. So that does work very well. We start getting into zinc in here. We are going to be pushing the limits of some of our water quality criteria. Because again, even at the small things, we're still looking at having to deal with small particles. That's may change that focus of treatment to this idea of how do I remove things that are very, very small. So again, we can see that part of it. And again, taking a look at that, this is other sites in there, and here is the one from Southern California coming across. Cadmium, very well associated particulate fractions, copper, zinc, not so much. Here's the total. Here's the less than 0.45 micron. They're a lot closer, still okay. But if I had to remove thallium and antimony, which I had to do, they're actually heavily in the dissolved fraction, which does mean I've got to go back in and look at removing basically dissolved ions or things that have basically attached to particles that are 1 micron, 0.45 microns, or smaller.
I was going to ask a question about the zinc and the cadmium. Since they're related ionic size and stuff like that, why is there separation like that? Is zinc more soluble than cadmium?
Zinc is more soluble than cadmium. I didn't go into this. There's a longer discussion on this. And you can run the models, and this is one we don't get a lot into. You'll see it kind of mentioned in the slides. But I did pull it out for simplicity. What we really don't look at is these things are not ionic in terms of that Zn plus 2, Cu plus 2. We all remember from chemistry, basically dust off that memory. They complex. There's a huge amount of complexation that's going on in the environment. Is it zinc, cadmium, but cadmium's not quite as much, zinc, copper. They actually react with and create complexes with the hydroxides in the water, the OHs. But even better, they do it with phosphate, and they do it with nitrate. So there are copper nitrate complexes, there are copper phosphate complexes, there are zinc phosphate, zinc nitrate complexes, zinc ammonia complexes, which make it very interesting because, again, they may change the charge state, the valence state on that. So you might not have that +2 ion that you think you're sitting there, that little small ion running around, but you've got a much larger molecule, and it might be neutral, but still soluble, or it might be +1. And again, without getting into, let's see, much longer workshop, without getting into that, it makes that treatment choice a little bit more challenging. As people have particularly tried to use zeolites to do that in an ion exchange resin, which works very nicely in industry, doesn't work so well in the stormwater field because now you've got big molecules that don't fit in small spaces in the lattice work.
I would put zinc and cadmium in the same category.
It's a complexation. A lot of it's complexation. Some of it is complexation. Yeah. So again, it's one of those. It is zinc is typically more soluble. It typically stays more soluble and more likely to show up as in that dissolved fraction because again they do. It also binds really well to organic matter, and again that travels. So a lot of it dissolved organic matter. Zinc travels really well with it. So yeah, sure.
Are any of these temperature sensitive so that if you were going underground, you might get better removal?
I don't know enough to answer that question. In terms of, we haven't done a lot of temperature analysis, and I haven't seen anybody who's really done it in terms of the separation. Typically, we're operating in a fairly narrow range for temperature reactions. So I really don't want to answer. I don't want to take a guess on that part of it.
So is your question if you're doing that type of analysis from a stream or a river versus if you're going underground to like an underground well, you might have differences. Is that what your question is?
I was, given that your choices are kind of above ground or below ground, there might be some value to going below ground.
You're below ground. You're going to be much more temperature stable. Obviously, that's
cooler in general.
and cooler. I don't know that it's going to make a huge difference in terms of. I think there's so many other variables going on. I think it would overwhelm it. Like I said, I haven't looked at it. I haven't seen anybody look at it, so I can't sit there and say there isn't an impact.
Okay.
But the variability between storm to storm on the same site, and even in terms of what's dissolved and what's not, depending on what's washed off, it ties into rainfall energy in terms of how it dislodges things, how things react. Time residence in a pond or in a underground storage facility or sedimentation basin will affect it. So there are a lot of things that are going on that I think would overwhelm the temperature impact. That's my personal thought.
Okay.
I don't know that we could. I don't know without a multi-million-dollar project we could actually even tease it out because there is such a variability. So I do know if anybody has sat through Rob Travers and his students' discussion, I know from an infiltration rate standpoint, temperature does make a huge impact even over temperature ranges we see summer to winter in this area. And they actually see it in terms of infiltration rate because of the changes in viscosity of the water. And so so if you actually test your basin in summer versus winter, there's actually a cyclical infiltration rate that seems to be going on that if you test in the winter, you think it's failing, and it may not be. That's consistent testing in the seasons. So, Michelle.
Does pH have an impact on
Yes.
the dissolved? And are there things, I'm thinking, are there things you can design into your site to adjust the pH that would help?
There are. I'm going to go back to the statement of, and I'm going to show some treatment devices that are definitely much more geared toward that. Some results, preliminary results. And there are people who are doing it who are trying to create precipitates. The question, and for an industrial site, that may be worth it. Again, it's one of those challenges they're having, and I think of the one I'm trying to finish up a final report for. Adjusting the pH in order to get it out, to precipitate it out, but then you got to bring it back down to neutral before you discharge. The question is it worth the cost of that transfer? And that's always a debate. An industrial site, we are dealing with heavy concentrations of metals. It might be.
Okay.
And so,
how broad is that pH adjustment? Are there things you can do in your site that?
some of the ones that have tried limited amount, if you're trying out in the field, have been things like adding gypsum. But mostly I've seen the gypsum addition used to try to change the effects of road salt. But it's changing the pH. Certainly typically, and this is not for all of them, typically metals are more soluble in acidic conditions, particularly in these slightly acidic conditions of most of our soils around this, at least around central Pennsylvania. Yeah, it's not a huge amount, but again, looking at that versus complexing, we're dealing with a whole set of interesting challenges in here. But pH control certainly has to be considered. If I'm an industrial site and I'm looking at a map at Southern California discharge permit, pH might be on the table. I certainly would not dismiss it as an option. So we didn't look at that, and I'll get to that in a minute. Because again, what I'm going to make the point is if you don't look at, like looking at a sand filter where it was chemically inert, because again, in an industrial site, yes, we do have bacteria. It takes a long time for a bacterial biofilm to develop. And more likely, because of the metals concentration, we're going to keep it very low because it's going to hurt the bacteria. They're not really used to those high metals concentrations. And you'll see, here's our sand filter looking at copper and our hydrodynamic separator. And blacks are our unfiltered total samples, and then the reds are filtered. You can really see on those, there's not that much difference in terms of removal. And they're pretty much on the N equals outline, or close to just barely below the N equals outline. So again, a biologically inert filter, or something that doesn't have like an organic material to it, like a compost, a peat, or whatever, may not get us to the metals that we want, may not get us what we wanted to see. So again, there's a very disappointed site owner right now. Because he did this. So there are some things we can do. Again, large particles, we can settle them out. There are the association questions that came up for some sites, and I can think of a few, scrapyards being a primary one. Typically, we tend to show up with metals showing up in, a lot of times in some places, with larger particle sizes. Others, and we've seen it more on airport highway hangars, highways on guardrails, as at airports, typically the metals are associated with smaller particles. Again, that's been that interesting challenge. So again, what do we end up doing? Trying to deal with that. We can try ion exchange. Again, if it doesn't, something like lead that doesn't complex well, ion exchange might work very well. Our zeolites are, and some of those things. Otherwise, we're looking at what we think in our manuals without the plants. Things like a mix of a sand and compost filter will get us some of that active, chemically active media that we need, and that can still go underground. So again, there are a lot of different types of media out there, and that's what we'd be coming back in and taking a look at. Again, a lot of our, organic media, what I call non-activated, we have tried on some sites. They very specifically have had to, that California site, because of the dioxin, because of the thallium, we actually had to go to carbon, activated carbon. They've got a 10% activated carbon in their mix. The good part is, while it's expensive to get it, that it's at the size, at the quantities they need, they are not paying the fines any longer, so they're pretty happy about that part. So again, it kind of comes back in and deals with that. So, but again, we do actually get some soils, peats, and things like that. But is
a
it?
lot of clogging with the zeolites?
We have not, on the industrial sites, we have not seen a lot of occlusion or blocking of the sites. I mean, certainly it's a concern.
It's a cheap way to go for the ion exchange, right?
If you can do the ion exchange, the zeolites can be a very cheap way to go. So again, you go down to the store. There's plenty of companies that are selling perlite, which is a zeolite, and you buy it at your garden store. So certainly there are some options in there. Again, we get toward that those complexing metals, they don't work real well. So they don't do well for the copper and the zinc. You think they would, but they don't, and that's been the challenge we've run into. I've tried for 20 years to get the darn things to work, because I keep hoping, like, what are we doing? So, and again, we can improve that pollutant removal in there. In this case, by, for example, increasing that carbon, reinforcing that idea that having a carbon source at a reasonable percentage works without having, again, if it's soil or compost or whatever, without releasing nutrients, which is that balancing act in there. So again, coming back across. So again, back to the question came about clogging and about this. If I'm a design engineer, I'm a client, my client wants to get the smallest footprint possible and wants to get the water through and get out of the site. For them, it's a nuisance. Doesn't matter if it's a highway for safety, whatever it is, again, or an industrial site that has that part, in spite of the guy who said he just prefers to evaporate it. But there is this challenge in there because, again, if we're using anything that clogs any filter, that's one reason for the sediment forebay is to protect that filter medium, to try to get rid of that sediment as early as possible. And again, that idea of, filter, we lose flow rate over time. And again, yes, if it's an industrial site, they can go back out and clean it. If you have at a highway site, they don't really want to have to go out and maintain these things every year. When I've done design, we typically tell them that it'll last for 3 years, and we try to make sure from our design criteria it lasts for 5 to 7. Because I know if you tell them 3 years, they're not going out anytime soon. So that kind of thought process in there. But there is a relationship between filtration rate and chemical removal, because usually contact time buys us better removal. So the idea of high rate filtration system you can go back and look at, and I guess I can pick on them because I actually did some work for them. There are some upflow filters out there that are basically siphon operated filters that are sold by vendors. For some things they do very well, but the problem is if you're trying to get a lot of metals out of them, it is a challenge because they run very quickly, so there's not enough contact time with the media. Again, it's a great removal for straining particles. It does, if that's what you need, it does it very, very well. But if you're thinking it's going to get rid of small concentration of metals, it's going to have some problems. And they'll tell you that. I mean, I tell you, the vendor will tell you that. They're not going to lie about it. They've got the results. And actually, a good vendor about telling you what it does and doesn't do.
Does
So
multimedia filters give you the time?
It depends on your flow rate.
Yeah.
You got to deal with the flow rate issue. What's the contact time that you need? Again, that gets into a much longer presentation than I've got. I did go through and chop slides last night, and I cut some of those out. But what I really want to get to is how do we put this all together? We're really looking at potentially serial treatment devices. I mean, it's basically, in some respects, creating a miniature water wastewater treatment plant. And I'm going to show you some of our results recently from some of that work. The idea is that we can use device A coming in at a flow rate and an initial concentration, and coming out of device A is an effluent concentration. It's our influent to B, and then we use B for treatment. And so again, that idea that we use this building of different treatment processes to get where we want to go. So device A, and you'll see it in a second, would be sedimentation. Obviously would be whatever size sedimentation basin you want, whether it's a sediment forebay, and you see it now, even now in wetland design. Sediment forebays, that's exactly what this is. It's a device in series. And then the rest of it will be the wetland to treat the pollutants. You see it now in anything. Again, why a forebay? They says, well, you build a forebay so you can put all your sediment there, so you can clean it easily. Well, yeah, but it's still a device in series. So that's a great example in what we've been building for years that people are familiar with, that we've been doing the series operation without thinking about what we're doing.
So basically you put a baffle there typically.
Yeah, you see a lot of baffles. I've got some of that result I showed you for that sand filter was a baffled small sedimentation system underground and upflow sand filter. If I can talk. So again, that's the general idea. And then at this point, this can treat whatever you can't get in this. And going back to our example, this may not just pull out sediment. This may pull out some of our organics, our hydraulic oils that are associated with the sediment. It may pull out some of our metals. We can get some removal of some of those pollutants that are a concern. So it's not a wasted thing. It's not saying, okay, now all of our metals are going in, but now this will deal with anything we've got left over that we need to deal with. And hopefully this will protect that. If this is sedimentation, hopefully this is easily accessible. Even on industrial sites, my favorite trip to WEF is to go stand by the vac trucks. Decided one day I want to drive one of those Vector trucks. Yes. And so, but that's, you can go in with the Vector truck and clean it. And that's the general idea, is that, the Vector truck will work and you can get rid of that sediment out and you can maintain that more frequently. In many cases for an industrial or municipal or other authority, that's something they're actually used to doing too. This whole idea of new filters and installations and maintaining these things, as those who work in the green side of the business with plants and stuff know, this is a whole new world to these people. Again, this is something that, you got to go out and maintain a rain garden. I mean, the guy who maintains your sewer pipe does not know how to maintain a rain garden without a lot of training. And that's been one of the challenges we're running into. So again, if we kind of came in and said, okay, we'll just kind of assume we're going to get a 20 to 50 micron target, maybe somewhere between 1.6 and 5 gallons per minute per square foot. That's designable. It might be small enough. Again, I can pick my target choice for my particle size. And then device B, maybe something I want to do to get in there, again, looking at things that are particularly associated between 1 and 20 microns for the filtering, the physical filtering, and then the chemically active part of it, this compost, the soil, whatever, to get the rest of it. So that I'm not discharging something that's going to violate my permit. Because again, while we haven't seen in this state numeric permit limits, there are areas of the country where that's coming in. I don't know how long it's going to take the land of fruits, nuts, and flakes to migrate their ideas here. If I refer to my friends in California. But that there are numeric permit limits out there. I'm in the Chesapeake Bay Basin. In some respects, we're almost just waiting. When TMDLs come in, and they marry TMDLs in stormwater management, and that has a waste load allocation, the question can be, how is that going to be pushed back out? And I don't know. I'm not in the state government. But
We're doing that a lot in Southeast Pennsylvania, and TMDLs.
right, and so trying to tie those two together.
But DEP has put off all the plans on that because they don't know how to evaluate it.
That's going to be the challenge. I mean, and that's where it is that, and what California's done is you have to monitor every storm. And so again, for a major industrial site owned by Boeing, that's not, it's a burden, it's an onerous burden, but it's not a hard, but that they've got the resources to do it. As opposed to, your mom and pop, gas station or whatever, that type of thing. So the challenge is each of these has different media. Obviously inefficient to put multiple filters in series, so we do go back to combine the media in there. And taking a look at that, again, here was our example, our Southern California site, total, dissolved, and our permit limit. So notice I'm still going to have to come after a little bit of lead, some copper. I'm okay on zinc and dioxin. They just, yeah. But to kind of tell you that I'm thinking about designing my filter to look at these guys, because I've got to get from 7.5 to 5.2 and down to 14 to discharge. And I know that I'm at 0.45 microns, I'm at 20. So I'm above my permit limit. So I know I've got to get into something. Sedimentation isn't going to get me there by itself. So I've got to begin to design for that. So now, of course, zinc's going to be met if we can remove all the particulates 0.45 microns and greater, which we really can't do by sedimentation. That's that clay that never settles, that cup of red water. But I figure if I can get those, if I can deal with the others through a media filter.
Is it pay to use flatulence to drop that out?
I'm actually going to show you a result that says it may. That's a cost-benefit analysis that I'm not going to go into in terms of I don't know where it pays off and where it doesn't, except that the site I'm going to show you the results from where they did and got really good results is in Southern California.
Does that reduce maybe the space too?
It does. It tremendously reduces the space. And you'll be glad I graphed those results last night. No, actually, our filter design actually got it.
Okay, so you're good.
We were good. I'll show. I don't have the data in here, but it was a mixed media filter, and that was where we had to have the carbon. So the site owner at that point had to pay for the activated carbon in the filter. And so for us, it was a balancing act of carbon gave us problems on other media, on other pollutants. Well, so we had to mix it in, again, one filter. So I'm going to show it for copper because copper is more common. So here's our dissolved copper example. We have granular activated carbon, peat moss, a volcanic rhyolite sand, and a zeolite, surface modified zeolite. Taking a look in there, and you can see this is a fraction of effluent to influent. So again, where do we want to be? Again, obviously you can see if it goes above 1, we're actually adding pollutant back to the water that we didn't have earlier. So again, as you can see very well, nicely, GAC worked very well for this. Carbon actually got our dissolved copper out fairly well. Peat didn't do quite that, not quite as good, but it still we had removal. The sand did okay, so that's great. And again, we model predicted back to the question about the valences. When I ran the models on it, we only had 25% of our copper at +2. 65% had no charge. So if you're going to, zeolites don't work because it needs a charge difference to do the attraction. So it needs some of that. Same thing for any of the ion exchange resins. So that's where they really need the charge difference. Again, same thing for the sand. The modified sand needed a charge resin and all that. So that's why they didn't work as well. Because again, we didn't account for the ways that things are in the water. Our simple chemistry, Chem 1 class you took in college, doesn't go that far. So again, that's why we're trying to take these results that are very technical and challenging and complex and boil them down into a water quality chapter that I still have to write. So, okay, come on.
The problem with the copper was the random activated carbon was the layer. It gets the layer, right? It drops the efficiency. You have to
We actually mixed it in. For this large-scale site, we actually brought in cement trucks. Cement mixers work really well at mixing things. Yeah. It does. I mean, it didn't have. We just tried to get it reasonably distributed. But so what we did was start looking at the combinations because again, while carbon worked really well, it's expensive, but it caused problems with phosphorus. We had problems with phosphorus on the carbon coming out. We also had problems with one of I forgot which metal. I think thallium coming out. So we looked at what if we combine the modified sand and the surface modified zeolite? Do we get anywhere? We got a little bit better, but not much. Let's take that mix because these two were cheap, and they did really well on other pollutants. What if we add a little bit of activated carbon? Look what it did. That's 5 to 10% carbon. So not a lot of carbon, not a lot of expense. We cut our expense down. A carbon filter didn't get us there by itself for all the pollutants we needed. But we mixed it. So going back into that question, if we add peat moss back in, it brought the copper back up a little bit, but it actually gave us a benefit for, I don't know which one. It gave us one. I'm thinking, did I have it on here? Gave us plant life support, and because these were actually outdoor bioretention systems, so it gives us a little bit of support for the plant life, which we didn't have.
Activated carbon is because some of the metals might be amphoteric.
It could be. I mean, that's we didn't go in and explore that issue, but yeah, and that's that's what we were thinking was going on. So, but there is quite a bit of interest in that part. But again, the message I want to leave for those who don't want to get into the detailed chemistry discussion is sometimes the mixes work. The idea of having the mix in here when you're looking at multi-pollutants on a permit list, that it's not going to be one size fits all or one media fits all. And that's where the site investigation paid off in the long run, is that we had a better handle on what was going on at that point. So again, that's where we came back in. And going back to that idea of treatment trains, this is looking at a surrogate for organics chemical oxygen demand, which is fairly simple to measure. And this was a proprietary baffled sedimentation device, influent and effluent, and then a dry retention pond. And you can actually see that the pond gets us somewhere. We did okay on the sedimentation device, but it gets us somewhere. But to kind of give you an idea, here are the individual storms graphed out. They're all over the place. It took 10 to 12 storms to 15 storms to get us to have a handle on what even that variability is in there. So again, coming back across. Start putting these back up here. That's the same treatment train, a baffled sedimentation, proprietary device, followed by the dry pond. Here is a site-built sedimentation basin, influent post-sedimentation basin. That's our coagulation, proprietary coagulation system. Okay? And then this is a proprietary filtration system. I'm trying to remember. I think that's using alum, not ferric chloride, but I have to go back and look and see. This is a carbon perlite filter mix. So it kind of gives you a feel for what that's doing. Again, this is an industrial site, heavy industrial site. As you can tell on here, this is not so bad. This is zinc total. Well, except for this site where the influent concentration was medium was about 14 milligrams per liter. That's not micrograms, that's milligrams. So, which has been commonly found, my favorite concentration coming out of Seattle Tacoma Airport on their roofs and their guardrails. So if anybody's ever gone back and looked at the Seattle data, highway guardrails were leaching off zinc at concentrations in the 10 milligram per liter range. So but that should give you an idea of what we have. Again, you can see, go back to the question about the coagulation. Yes, we do buy some benefits of that.
You have 15 minutes.
Okay, and I'm about 3 or 4 slides from being done, so that's even better. So again, you can see it also, here's copper. Again, our coagulation did really well. I would ask the question that came back up earlier, should I use coagulation? It works really well. Do you need it that far? And that's what any site owner have to balance, is the cost of that. So I don't have a cost. With the, are we at the permit limit, or what we need for discharge? So again, it's going to be that balancing act. This is obviously a much cheaper system to build and operate. Baffled sedimentation device, take a vacuum truck, vacuum it out. That's our normal pond. Come by, he had enough site to have a pond on that site. It's a fairly large pond, so he was in good shape with that. If this gets us there, maybe we don't need anything else. And this is something we're very familiar with, building ponds. We're really good at that. You know, but again, where do we get to? Do we need that? Southern California, welcome to the permit limit. So, yeah,
That'd be good for the coagulation, be good for phosphorus.
Yes. Yeah, I didn't put the phosphorus data in, but it's really good for phosphorus. Certainly, like I said, it works very well. So again, it kind of gives you an idea of where our effluent was coming out of these guys. So it does become, and again, I can't tell you what it is, but hopefully we're generating data and looking at these things that we've been historically using in water and wastewater treatment plants, and looking at what happens if we can size them down and size them for the systems we're looking at. The filtered version, the pond doesn't get us anywhere. The baffled sedimentation doesn't do. I mean, there's very little. We dropped out. Most of it came out as solids that settled out in the sedimentation device earlier. But if I have to get into that dissolved fraction, we don't get much out of it. But the coagulation certainly may be my, that's when we start getting into that question about, is it worth it? If I've got to get, from here to there. This one we had an interesting problem with, a couple of high samples. Because again, it's a sedimentation basin, and it actually scours if it gets down too low. So they were scouring out previously trapped material. So surprisingly, our filtered fractions got to be very high on that part of it. But you can see also the filtration worked really nicely.
So that means that they have to clean it out or replace?
They clean it out fairly regular. They clean out fairly regular. What they do, the site for this guy, Southern California, they hold the water as long as they can. They try to use it on site for non-potable uses for dust suppression. If it gets down too low and then it rains again and they fill that basin up, it scours. Their concrete basin scours the bottom of what's been trapped. They do try to not put that back on site, but it's also, it's an interesting site. It's a really interesting site. And again, coming back in, you can see that same thing for copper, is that gives you an idea. Again, it's a balancing act of what do you need. I sit there and I talk to people and everybody's like, oh, I want clean water, so let's do this. I want clean water too. But I'm also an engineer, realistically going, if I'm looking at this, what is safe water? Both for me or if I'm discharging off site for the aquatic environment. If I'm looking at TMDL, is this okay? Is this okay? It may not be. So at least now I know I've got options if I have to go to driving to a more expensive, and it is a more expensive treatment. Every one of these two treatments, this requires no gravity, no operator, periodic cleaning out. The gravity works. You run it through that, gravity flows over into the pond, discharges off the site, nothing. These both require operators. This one requires the influx of chemicals. And again, trying to deal with also sludge removal. Substantial amounts of sludge removal. This is going to have a periodic media disposal cost. Whatever time you need to clean out, they clean out. I think if I remember, they change it out about twice a year.
When they remove sludge from something like this, where does it go?
They actually test it. I don't remember it. I think this site actually has hazardous waste. It actually has waste. I think it is. A lot of our media filters we've tested on highway sites and maintenance yards have not required it to be hazardous waste. We'll go to a municipal landfill. There are tests out there that you can do, send out to the lab typically to see if it is, even if you're cleaning out your normal, if you've got let me just use the rain garden example, a rain garden on a maintenance yard site, say a public works yard site, you probably might still have to check and see if it's going to be hazardous waste or not. Typically, again, that's, and it's going to depend on what the concentrations are in the soil itself that you're trying to dispose of.
If you used,
Harrisburg, you can send it to the incinerator. They need fuel. No, you got to deal with the hazard. And again, it's a borderline. A lot of the ones what we've really found in the field, and I'll get back to your question in a second, we found in the field is a lot of our sites, they physically clog, the sediment gets to be so much in there that you can't dig it out and replace it or scarify it enough to get the flow rate through, that it never builds up chemically that much because of the fact that because again, it just clogs. And so we actually stay below the hazardous waste limits, which is from a disposal standpoint, a good question.
If for physical separation, then adding plants, lilies, whatever, in a basin, that work. But if you have to deal with some chemicals, will the plants interfere with the chemical processes?
Well, this doesn't have this basin is a hole in the ground with concrete, so it's not planted. Again, it depends on how well your sedimentation after your coagulation is, just like a treatment plant. If it settles out pretty well, you would be discharged. Your post sedimentation at that point would be low concentration.
So you're using coagulation, and after the coagulation,
You got a small mini sedimentation.
The plants to get rid of the phosphorus or something like
You could, but again, coagulation is going to usually get rid of the phosphorus. Both alum and ferric chloride are really good at pulling phosphorus. So dealing with that part of it, that's okay.
Do the permit limits for copper reference pH and its bioavailability, like in the aquatic system?
Not in the one that we've been dealing with. Should they? Yes.
This one.
That's the interesting challenge, because you are starting to see that coming out of the EPA aquatic criteria has been pH issues for copper and for ammonia, because those are very pH dependent. So again, kind of giving you an idea, just going to give you a quick look at this since I'm going to be running out of time. When you put in new media, just to show you, if you actually break it apart, we had this challenge with that. We took some soils and tried to use them mostly intact, but we had a problem with it not fitting in the columns and pulling away from the sides. We broke it up. We had initially really high discharges. You're talking like 100, 200 milligrams per liter for the first few storms of nitrogen discharging. Because again, you're breaking the cement bonds in the soil by breaking it apart. And so that's why we do on a lot of these basins start seeing all these rain gardens do see high initial nutrient discharges. They don't last long, but they do last for a while. So it's one of those things to think about. That's helpful. At some point too, our soils fill up, our media fills up, and it goes back to that question about hazardous waste. Is this at this point a hazardous waste? And that's going to depend, again, and something's out in the field. If I was to put a rain garden out here in this parking lot, I'd say probably not, because it's probably going to physically clog with all the dirt and stuff coming off the cars before we have to deal with that.
And because it physically clogs, you're going to replace it.
Yeah, because again, we've tried like removing the top 6 inches, replacing that. At some point, that quits. That just doesn't work any longer. Plants buy us some time. Plants are great because the root structure will help us a lot. But at some point, typically, we do physically clog first. And then there's this part. I don't know how you guys did, but we really enjoyed our 30 inches of snow. I have a Corolla. I have pictures of before the last 8 inches that you couldn't find the Corolla already. So again, just to kind of leave you with this idea, this was a soil. We added a compost mix to it. Interestingly, we don't think about the compost tends to reduce the flow rate. The higher the compost concentration in the soil, the more we actually saw the flow rate in the soils decrease. We saw clogging, structural changes, biofilm growth, something in there is going on that, what?
Because you're breaking it down, what's going on?
We actually think looking at it as biofilm. Because we've actually got a biologically active. So it makes that difference about trying to balance out this issue, either not letting your highway department dump their piles of snow in your roadside rain gardens, or good luck with that. I've tried that on campus, it doesn't work. And also that idea of balancing out, how much do you need? And this is where I come at it. Is compost, all of that soils give us a great benefit for plant growth. But if you go back in, we're starting to realize that we've been telling them, because the horticulturists told us to put a lot in there, because they like the plants to grow quickly, that we need to back off of that from an environmental and a treatment standpoint. So that we need to come back in.
Are you talking about the compost on top of the soil? Or
Mixed in. It's a mixed soil. You go back and read the manual. So the manual itself, I find what it's like. Now it's come down to, I think it's like 5 to 10%. Even 10% starts getting a little bit high. And the other challenge we have with that is that road salts, these soils have these metals attached. These are actually ingrained. We didn't add metals to this. We're doing that experiment now. This is just what was in the soil naturally. Road salt, sodium chloride, is a great ion exchanger. It actually washes off previously trapped metals. So think about it. Here you spent all summer picking up and collecting all those metals that you got off your roadside, off your industrial site, and then here comes winter, you put some salt on them, and they all flush down one more layer down. Eventually, they're going to get to the groundwater. So they do a really good job. So yeah, your topsoil is now clean again. as long as you got flow through the salt, but just something to be thinking about that it displaces what's been previously trapped. So again, if you've got a very shallow media, at some point it's going to get into your drainage system and discharge, and they're going to be released. If you're going to groundwater,
Nutrients too, that are like the phosphorus that's found, it
Yeah.
washes off of the salt.
yeah, not quite as, yeah, yes it is. If you want it, I'll send you the paper.
Yeah. You know, all this.
And ask questions. I know, Michelle. So that kind of comes back in. And I guess the lesson, I'm glad you guys asked questions through this, so I know we have a formal question much of the time. But really, it's industrial sites, highway sites. Highway sites are probably getting much more generalized, but industrial sites, we're really going to have to be looking at them by industrial classification, in some cases by site. That there is an investment in that, that's time. Our treatments are not what we're going to pull out of the manual straight. We can use those same concepts, we're just going to need to adapt them for what we're dealing with. And again, it's going to be interesting as the states, the regions, EPA start trying to address this little big, ghost in the room that our traditional manual that looks at TN, TP, and TSS is not going to address. And there's a lot, and unfortunately, I think it's an underrepresented, underserved area of information that we don't have great information for. Fortunately, some of the industrial associations are beginning to put money behind looking at what will work for their clients.
And do you use this, I'm sorry.
Does EPA have guidance, given their
No.
broader? Okay.
No, I mean, not good guys. I mean, a lot of it's best available technology. Others, you've got the jurisdictions like Southern California, where the water quality control boards are writing permits.
You're stuck with the state.
Some of the state manuals. But even that, if you go back and look at where EPA is collecting data on, a lot of it's been from treatment, has not been as much on metals and organics. They've done a bit with it, like highway runoff or thinking about petroleum hydrocarbons. So there's a lot historically going back. The unfortunate part, and I've seen this with EPA, is there's a lot of stuff they published years ago that's not easily available on the web, so they're rerunning the experiments. And they have a limited budget. I'd like some of that money to not redo things they've been doing, but do new things.
Taxpayers' money.
Yes, and so there's a lot of historical data that's out there that I wish was more publicly available.
In our region, there's a watershed outside of Philadelphia, that it's the nitrate, the nutrients, they're focusing on sedimentation first, and then the next set of TMDLs coming through will be the metals.
That's what we're hearing too. I mean, of course, I'm in the Bay watershed, so they're right now they are still focused on nutrients and sediments and some bacteria. Seems to be the highest priority. So, but they are at some point. This, like I said, California is focusing on everything. So.
EPA commissioned a study down in Maryland on the in-stream sand filter structures that biohabitats has been doing. And
Yep.
They had some really good results
Yeah.
out of that. Is that affecting you guys anything to work with, or is it not really applicable?
It doesn't apply as much to us. I mean, some of it, they definitely have gotten some great results. I mean, that's been the nice part about seeing that. We're always looking around to see what people are doing. We haven't figured out how to modify or adapt some. I mean, we've certainly been using sand and other media to deal with pollutant problems. My problem right now is that as they start putting stuff out there and getting great data, it's the time my projects are wrapping up and I have no funding to continue on with them. So we have that gap disconnect. So, I mean, there are always new ideas. It's always a great way to do it. And it's always good for something like biohabitats and other companies and other sites. And whether it's government, private consultants, whether it's industries, municipalities putting their information out there.
They found by mixing in wood chips, the microorganisms would keep it all from clogging up. I don't know if that would work in your side.
Actually, wood chips have had a mixed bag historically, in terms of they've also been known, if they are not, depending how well they're mixed in, if they don't get mixed in well. Same thing with newspaper shreds. They always try to do that to provide a stable, slow degrading organic carbon source. Is this idea that it would clog, actually cause clogging problems. So they've had mixed results. Some sites where it's worked very, very well. So I don't want to sit there and say it's not going to work. But there have been others where there have been problems. But we've had the same thing happen in rain gardens that don't have these things. I mean, so it's been that interesting challenge. My philosophy is at some point, hopefully the research continues to go on, is that we've got to keep doing this. We got to do as much as possible to do this right, because we're not going to get too many chances at this. If you tell somebody they've got to put in spend thousands of dollars, hundreds of thousands of dollars to put in systems to deal with this. If we screw this up, they're not going to listen the next time we tell you I'm going to come back in and fix it again. Not happily. And so that's always my concern. That's my big concern with the TMDLs is that if these things, even the state manual, Michelle's heard me rail on and on about it for years. Most sites we can't get 85% removal.
That's the argument the municipals have been making with Dick, and we're going to do all this expensive work, and then if water quality doesn't improve, you're going to make it
Right.
do it all again.
Well, and that's the challenge is that most of us don't really, who are in the field and who deal with water quality data by itself, don't believe the state manual percentages. And so what happens if you don't? If you're using that to say, and water quality doesn't match, how are you going to go back and tell the public and that we're going to have to come back in and change things and improve
Our
them?
area, the EPA is going from 24 phosphorus down to 0.1.
Yeah.
Sewage treatment plants have gotten 60% removal so far, but they can't go. So it's like adding a major cost to get an extra few percent. And I'm just wondering what things you can use to in place of phosphorus standard. The state doesn't have a phosphorus standard anyway.
Yeah, we're starting to see phosphorus standards coming in a little bit. The push of, at least in the Bay Basin, try to get rid of phosphorus in fertilizers. Of course, the Bay Basin, our side of the Bay Basin, we're actually nitrogen problems. Most of the Bay Basin, the Chesapeake Bay Basin is phosphorus. We're nitrogen, which is a lot of fun to try to treat because we got a bunch of cows. Lancaster's population 11-to-1 cows to people. And it is a bit of a challenge, but it is. Those are going to be the problem. I mean, I facetiously tell my students it's our Employment Act. That idea of going in through enhanced nutrient removal is really going to ENR. It's going to be that's a huge upgrade on plants. It's even worse for trying to get nitrogen down that low. Then I continue to move that nitrogen standard down. It's a huge problem. I mean, it's a huge challenge. And I don't teach the wastewater side. I've got colleagues that do, but again, a good chunk of their class is these hugely advanced systems to do this, and why you're seeing nutrient credit trading becoming, very much of a push at some point in the Bay Basin. I mean, it went through a quick phase, it kind of died off, and hopefully it's going to resuscitate as they try to bring things back online. But that's, City of Harrisburg got a huge flack for deciding to purchase credits while they upgraded their plant. But their logic was, and I've talked to them, I think it's a reasonable logic, which was if they try to go out in the market and find a contractor and a consultant at the same time that everybody else is it's going to be very expensive. They can wait a couple of years. The cost will come down per incremental time. And that's what they did, was they enhanced their treatment for a little bit. So they did do some upgrades, and then they purchased the rest of it on credits. I can't sit there and say they're wrong, because they had treatment plants that went through and did do that, yes.
But bioremediation work for the nitrogen removal?
Well, I mean, you are looking at biological removal to get rid of nitrates. That's about the only thing you're going to do consistently. There isn't much. There are very, very few carbons that will do nitrate for a very limited amount of time. So it's all biological. Whether it's plant uptake, whether it's microbial interactions, that's always that challenge. I mean, that's what the whole enhanced nutrient removal is enhanced biological removal in a treatment plant. And so one of the challenges we're trying to do is figure out how do you transfer that into something out in the field that doesn't require power and that is low maintenance. Because that's really the stormwater question. How do you not have to run electricity out there? Industrial sites have the advantage of electricity. Highways don't, residentials don't. And how do you do it at low maintenance? Because we know what the maintenance time frame is, which is not what they report. So I think we're getting there. I found those several years ago. I still like that. Yes, I'm in the Bay Basin. I like crab cakes. So I think I don't know if there's time for questions or if we're time's up. It looks like we're only in the holidays. And so I think I'm out of time. Thank you all very much. I hope I gave you something to think about.